Hello, this is Mahanda Didia. This is continuation of Module 10 on formulation and composition of suspension formulations. In this submodules, we will look at auxiliary agents. Auxiliary agents are critical to stabilize suspension. pH and buffering agent. As pointed out in earlier video, buffer systems in suspensions are used for several things. Number one, to control the pH. Minimize solubility of the drug. This is very critical, and we'll look at that in more detail in this submodule. It controls stability of the drug and also ensures compatibility and stability of other ingredients. Focus is on minimize solubility of the drug in the vehicle and thereby allow the drug to be suspended. Example here is naproxen sodium suspension. The suspension pH is between 2.2 to 3.7. Naproxen sodium is practically insoluble in low pHs. However, if pH increases above 6.8, its solubility increases as shown here. So in order to make suspension, we can lower the pH in this range here between 2.2 and 3.7, and it would have very low solubility. As it's administered, pH of 6.8 is attained in intestinal fluid. Naproxen sodium will dissolve and available for absorption. So this is the principle used in naproxen sodium suspension. Let's look at the second example, Ciprodex otic suspension that's used for the treating ear infections. Ciprofloxacin has low solubility in neutral pHs. And second ingredient, that's dexamethasone, is sparingly soluble in aqueous buffer. So these properties are used, and otic suspension pH range is 4.5 plus or minus 0.2, where ciprofloxacin solubility is very low in vehicle, and ciprofloxacin together with dexamethasone can be suspended. So here we see the usefulness of pH and solubility profiles. This type of data, solubility pH, is generated in pre-formulation. Data is provided to the formulation scientists they use in generating suspensions. Another way to suspend the particles is Rheology modifier and structured vehicle. Suspendability of particle is essential for uniformity of the product, uniformity of the dosage. Rheological modifiers, they change the viscosity. The sedimentation velocity is decreased by increasing the viscosity. Structured vehicles work by changing the viscosity. Particles are suspended. Once we provide the shear stress by shaking, shear thinning, so the flow is improved. And when we put the system back, structured network return. So once the structured vehicle is shaken, viscosity will decrease. So rheological modifier structured vehicles are used to improve flowability of the product. Readers are requested to refer to Module 3.2, Physicochemical Characterization, Sedimentation. Examples of rheological modifiers are cellulosic derivatives, clays, polymers, acrylic polymers, polyvinylpyridine, and gums. At storage condition, the suspension are at zero shear viscosity, and at the zero shear, particle will sediment. However, when we apply shear to it, high shear, particle sedimentation will change. Stokes' law can be used to calculate the velocity. Let's look at the video to see what happens at zero and high shear viscosities. So zero shear viscosity is when the material is at rest. There is no shear, but we can measure the viscosity and we can apply very small shear stress, and there would be a plateau, and this plateau is called shear. You have the different samples. Sample 1, 2, 3, 4. As you can see, sample 4 has a less viscosity. As shown here, zero viscosity shear particle will settle, high shear particle would settle slowly. Flocculating agents. Flocculation forms loose sediment and it's redispersible upon shaking. Flocculating agents help suspension particles to link in a loose agglomerate or a floc that is easily redispersible. And we looked at zeta potential in the previous videos. The zeta potential is high. It will form a deflocculated cake sediment. If we neutralize that charge by adding flocculating agents such as potassium chloride, calcium chloride, aluminum sulfate, it will neutralize the charge. It would produce flocculated sediment because repulsive forces between positive and positive charge have been reduced in this system. If we add more flocculating agents, it will change the charge again and it will become deflocculated and cake sediment. So this model is common. One needs to optimize the level of flocculating agent. Another model is polymer. So we can use polymers. And if we use polymers with a good solvent polymer, they will repel each other, will not form the floc, and it will form deflocculated. If we have a poor electrolyte flocculated with polymers, it will form a floc. Particles will come very close to each other. They will not be repelling, and it will form a floc. These two models are commonly used in pharmaceutical preparations. Here's the data generated on zeta potential. Zeta potential increases slowly as we add electrolyte. In this case, alum or aluminum sulfate is increased in parts per million. And zeta potential is measured. As you can see, zeta potential is increasing. And there are two different particle sizes, fine and 200. And zeta potential increases in both cases as more aluminum sulfate is added. Eventually comes to 0 from the previous discussion. Zeta potential close to 0 plus or minus 5 will produce flocculated suspension. Zeta potential of large numbers will produce deflocculated suspension. Flocculated suspension will sediment relatively fast. Deflocculated suspension will take longer time to sediment. And it's shown here. Sedimentation rate of flocculated and deflocculated suspensions are shown here. As zeta potential increases, the sedimentation rate decreases until zeta potential is around 0. And then as more aluminum sulfate is added, more and more negative charge is accumulated and zeta potential is increased, sedimentation rate decreases. We need to optimize zeta potential and flocculating agents. Preservatives are required because of water. Some of the suspending agents supports microbial growth, and sweeteners that are used in oral preparations support microbial growth. Total amount of preservatives should be looked at, and loss of activity of preservative in suspension is important. Ionic materials such as sodium benzoate, interact and bind. If it's bound, that's not available. Paraben may absorb on suspension particle surface itself because of the charges and attraction. If parabens are bound, they will not be available for microbial activity. This needs to be included in the total calculation. The preservatives and their concentration range are shown here. Ethanol and propylene glycol needs to be carefully used because they may act as a solubilizer in suspension formulation. Benzyl alcohol, quaternary ammonium compounds, benzalkonium chloride, sorbic acid, benzoic acid, methyl and propylparabens are commonly used preservatives in suspension formulations. Organoleptic agents for oral suspension is critical. Oral suspensions have grittiness because of the particle. They need to be palatable. Otherwise, patient will not use them, especially children. So to cover the taste and the grittiness, sugar alcohol, such as mannitol and sorbitols, are commonly used as they give cooling effect. And the cooling effect reduces the grittiness feel of the particle with the sensation. In addition to that, flavoring agents such as grape, cherry flavors enhance patient acceptance in pediatric patients. Sweeteners such as sucrose and artificial sweeteners such as aspartame provide feeling, help reduce the grittiness. Sequestering agents such as they bind the metal ions, sodium EDTA, and prevent the oxidation of drugs and other ingredients that are present. Combined with the vehicle surfactants, pH, flocculating agents, rheological agents, and organoleptic agents provide suspension